when you stop to think of the number of quizzes we've had and that you get to wipe one out, some of you could be looking at 3-4% here, depending on how badly a quiz may have gone sometimes. So, just saying. All right, expected value. Your parents want you to study a bit harder. They offer you an option when taking tests. If you get an A in math, you get $20. If you get a B, you get 5. C's are 0, D's are you owe them 5, and F's are you owe them 10. If the expected probability of you obtaining grades in math based on prior information are the following, should you take this opportunity on your next test, why or why not? Stressing the why or why not part, because if this were a question on the quiz and you just put an answer and said yes or no, yeah, that's not going to work. So, what might be an idea on how to go about this? Or do you just risk it?
YOLO. I'm just kidding. You take the possibility of you getting an A, and you put that underneath how much you make.
Okay. So right. Well, I can either do 20, and I could use this as a percentage, as a decimal. Yeah, because it's not just you have a chance of getting one of 5 grades, A, B, C, D, or F. There's specific percentages that are going with each. Now, if I'd have said you had an equal chance of getting each of the grades, that absolutely would have been a way that you can go. But if they're going to give us the percentages, we really do need to go that way. So then for any grade that I'm going to get a positive outcome, like B is still a positive outcome. So it's always possible value times the probability of that occurring, whether it's a percent, a fraction, whatever it happens to be. Okay, C's being nothing aren't really going to do a whole lot for us. But then I've got to make sure when I get to the last two that are bad options for me,
Subtract. Boom.
that's right. I better make sure there's a minus in there, because if there's not, that's going to get me in a little bit of trouble. And then the F's, well, that we don't even want to really think about that, but we have to. So once I get that, I could type that all flat into the calculator all at once if I wanted to. Or I could punch them in individually and start to take a peek. And all I've done below there in red is I took each individual possibility and went ahead and multiplied those. So that's where all my numbers that are down below are coming from. And it looks like mathematically my expected value would be a negative quarter. So should I take my parents up on this mathematically speaking? No. Why not? Right. Okay. So my expected value is negative. That's not good for me. Now, again, this is mathematically speaking. If you know you've been slacking and you're for sure going to get an A on the next test, you may go against this anyway because you have other information that's going on. So just something to consider when you're doing these. Okay? But the idea of expected value isn't going to change because we're always looking at it, theoretically here. We're not looking at it, is it a class you're good in, bad in, did you just have a bad day? We don't know all those things. All right. Same type of idea here, number 2. Margaret Billingsley has just sent some construction plans to Europe via one of the overnight delivery services. 95% chance they will arrive at their destination by 9 a.m. the next morning, in which case her company will be awarded an $80,000 contract. If the plans do not arrive on time, the contract will be awarded to a competing company, in which case her company will lose the $10,000 already invested to drop the plans. Find your company's mathematical expectation or expected value. What do I do? Some mathematics, yes, that would help. Okay, good. There's a 95% chance, and again, I'll just use that as an decimal form, that I'm getting $80,000. But I'm going to lose 10,000 on the other, 5% chance I don't work. Now notice it doesn't say anywhere on there anything about 5%. I have to remember, oh yeah, whenever I'm doing expected value, all of my values have to add up to 1 if they're fractional or 100% if they're in percentage form. So if I already had 95, 5% is all I got left. And I got to make sure it's 0.05. So by doing that, so we got 80,000. So there's a 95% chance that's happening. So that would be 76,000 minus 10,000 times that other 5%, which is only 500. Like, where's that coming from? I see 75.5. I just did a little quick math to figure out what that would be. So that's pretty good. That is a pretty good chance of getting way ahead in the game here. But again, you notice it sets up a lot like the first one did. And then it's just expected value times expected probability. One more the same way, and then we maybe will start throwing a couple of twists in here. On a television show, a blindfolded contestant is asked to select one bill from a box containing money as follows. Denomination of bill, number of bills in the box. Should have had a comma in there. So there's 16 $20 bills, there's 10 50s, there's 7 hundreds, there's 5 500s, and there's 2 1000s. If the contestant gets to keep the bill selected, find the contestant's mathematical expectation. Okay, so do I just do 20 times 16 for the first one? No. What do I have to do if I don't do 20 times 16? Okay, what I have to do here is, yes, my expectation still would be 20, but I need to know how many total possibilities there are, because there aren't just 16 total possibilities. So I'd have to add all these up. And I notice, well, now there's 40 total bills that I'm working with. So when I'm doing each of these just each turn into fractions or probabilities. Now I can choose to reduce the fractions if I want to, because I'm just multiplying. I can use the decimal form if I want to. Or if, just for sake of jotting down what I'm doing, it's always value times probability. And in this case, it doesn't look like there's anything bad that could happen out of this. It looks like I'm winning something. It's just a point of, well, how much am I winning? And I'm not having to split it up with anybody. Sort of like the person in Florida that won Powerball Saturday. I was shocked there was only one person, but okay. So, if you go through and again, multiply those out, the one thing I always mention is be careful when you're doing this, because really the only way you can mess this up is if, well, you mispress a button somewhere. So if you're doing this for the first time, multiply those out and see if you're getting the same thing I am. But that seems sensible. Hey, all right. I can mark this off. Thank you, sir. Thank you, sir. So, if I were to do this contest 40 times, on average, I'd win about $150. So if I got to do this 40 times, I'd probably win about $6,000, somewhere there. Pretty decent. Not 600 million, but not bad. So then,
apparently 80% of the combinations are what? For the Powerball.
yeah, it's interesting to go back and look and see how many combinations are bought or how much people were willing to spend on trying to get as many of the different combinations as they could. Because typically as that goes up in value, you also start seeing more people playing, which is going to wipe out more of the possible combinations as well. At least most of the time it is. So, all right. Now let's see here if we can keep catching on to the little twists of these. In a raffle, 25 tickets are sold at $1 each for 3 prizes of $100, $50, and $10. You buy 1 ticket. What is the expected value of your gain? Whoever's running this raffle isn't doing this real smartly, but that's a whole different issue. So, okay, I see there's 3 possible things I can win. What am I going to be multiplying each of them by? Okay, right. There's 3 prizes. There's one $100 prize, one $50 prize, one $10 prize. But there are 25 tickets that were sold. So I'd have 100. I'd have a 1 in 25 chance at winning the 100. I'd have a 1 in 25 chance at winning the 50. And I would have a 1 in 25 chance at winning the 10. What's that? That's what I was waiting to see if somebody was going to say anything about. Because sometimes we get rolling so much, and we're going, okay, well, I see those 3 things, so I'll go ahead and I'll put these in the calculator, and that's basically going to tell me what I need because, well, I might win one of these. And we think of it a little bit like we thought about the television show problem up above. And the mistake we make is, well, we're not guaranteed a prize this time, and there also can be something else that we may need to keep in mind. Because at first you may think, ooh, $6.40, that's pretty good. But do my fractions add up to 1 whole? Not yet. What's up with the other 22 out of 25? I lose the $1 because I don't win anything. So again, whenever I'm doing expected value, I have to make sure my percentages or my fractions add up to a whole. So I still have to subtract those other 22 times that I am not going to win anything. But that's still pretty good. That's a chance I'd be willing to take for $1. My expected value is $5.52. Gamble 1 and typically you'll win back the equivalent of about 5. Yeah, over time that's pretty good. But you've got to remember that minus part because it may not say that every time. So then we start to move away from that a little bit. We go, all right, in a Harlem High School poll, 375 students were surveyed. 74% of them said they hated math class. What's the margin of sampling error in the likely interval that contains the percentage of the population? How do I find the margin of sampling error given how many people were surveyed? All right, 1 divided by the square root of the number of people that were surveyed. That doesn't change. So in this case, 375. And again, we typically just go to the nearest whole percent, which in this case would be about 5%. But that's only part of the answer because it says, what is the margin of sampling error? Okay, there's my margin. Exactly. We're looking for that range now, that interval where the likelihood is of finding somebody that's going to say that. So I'm going to take the 74. I'm going to subtract 5 to get to my kind of lower limit and add 5 to get to my upper. Okay, again, make sure you get both. Reading carefully gets to be the biggest portion with some of these. So margin and my likely interval. Still way too many, but hey, the data is the data. All right, to the back we go. Mr. Hardy says, many students will attend a graduation party in June. What is the margin of sampling error if the likely interval of those planning on attending is 19.5%, I should say 35.5%? How would I figure out what the actual margin was? It's sort of like working backwards from number 5. Okay, take the average of these two. Thank you. So, what we are going to do here is add those up and divide by 2. But please remember, if you are going to use the calculator and you're going to do this all at once, please use the parentheses. And I know some of you do use your common sense occasionally, but some of you get rushing so fast that you don't, because you're like, well, why do I have to put those in there? Well, let's see what happens. Let's see, the average of 19 and a half and 35 and a half is 37 and a quarter. Wait a minute, what the heck? Okay, when I don't put in the parentheses, remember the calculator is going to do order of operations. It's going to divide and then add. Well, that's silly. That doesn't make any sense. So again, you either need to use the parentheses, use your noggin, or do 2 separate parts to this to get your correct answer. Okay. Now, here's the other part. You're like, oh, so it's 27.5%. No. Okay, that would probably be the original statistic that you were given for this. They'd say about 27.5% of them are going. How do I figure out the margin of sampling error now that I have this? Okay, how far is it from each of my extremes? So you can either minus 19.5 or you can do 35.5 minus this. So let me scooch this over. So if I did 35.5% minus 27.5, looks like my margin of sampling error is about plus or minus 8%. Okay, so there's that extra step in there. I've got to find what probably my initial data would say, then figure out how far away that's going to be. So again, there's a couple of steps to these, and you do have to be careful. Standard deviation. Keep this simple. Again, if I need this, we're going to go calculatoring. So we're going to go to the stat. We're going to go to editing that first list. If you don't have anything, great. If you do, remember, if you go up to L1 and then hit clear and come back down, everything that's there will go away. And then just carefully type in your data for this particular problem. And again, at the end, especially since this is a shorter list, it's pretty easy to say, okay, let's see, I typed 10 numbers in. 2, 4, 6, 8, 10. Okay, I'm feeling pretty good that I have these in correctly. Once I get there, I go back to stat. Okay, my variance statistics under number 1. And I want to use, in my case, list 1. So second and L1. And remember, unless you are told differently, when it's a population, we are using this one. Okay? Not the sample, but the population one. So the one down below. And how far did I take this out? Just 1 decimal place. Okay. If you took it out to 2, called it like 8.65, that'd be okay too. But that's how you've got to go about that. There's really no other shortcut way around it. So be cautious when it comes to this. Let's see what else we got here. The mean life of a tire, that's kind of funny when you read it if you don't know what you're talking about. The mean life of a tire. Life's tires are mean. Is 30,000 kilometers. The standard deviation is 2,000 kilometers. 68% of all tires will have a life between how many kilometers going each direction? So 68%, how many standard deviations does that cover? 1. Okay, here's my chart. 68% takes me from -1 to +1. It covers 1 standard deviation each way. So, if that's true, if it's only 1, what's my lower and my upper limit going to be? If every time I move 1 away from the mean, which is 30,000, it's 2,000 heading each direction for each deviation, what's my number going to be when I shift 1 deviation to the left? 28,000 because I would subtract 2,000 kilometers if I have a negative deviation. What about if it's positive? 32,000. And that's the reading that you're doing into this, and that's the nice thing about having the little chart that we work with here. So 95% of all tires, ooh, there's 95%. So 2 deviations each way. So I could take this one and just say, okay, I'm going to move one more. Because I started at 30. One standard deviation got me down to 28. What's 2 deviations going to get me down to? 26. And then same thing going the other direction. If I was at 30, and I went right one, got to 32, what's my second one to the right going to be? 34. So I have to get kind of a feel in here for how this is working. It's not bad, it's just figuring out, where do I get the info from? What percent of tires will have a life that exceeds 26,000 kilometers? You're like, ooh, that's my -2. Okay, there's my -2. If it exceeds that, it'll be all of my deviations to the right of that. Do a little bit of this so we don't lose it. So if I take all my deviations to the right of -2, what do I end up with for a total? Bail me out. I said bail me out. Huh? Because I would just add. You're like, oh, he's added again with that stuff on the board? Yeah, I am. So let's see here. Now let's see if we can actually apply it. If a company purchased 2,000 tires, if a company purchased 2,000 tires, how many tires would you expect to last more than 28,000 kilometers? 2 parts to this question. Which deviation am I starting at if I'm looking for more than 28,000? Okay, -1. Because 28,000 was 1 deviation to the left. So my first part is, okay, what percentage of the tires are going to be good? Let's see, 68, 81.5, 83.5. So it looks like 84% of them are going to be good, but that's not the question. The question is how many tires are going to last. So how do I use the fact that 84% of these tires are going to be good? What do I do mathematically now? 2,000 times the percent is a decimal. So what is 84% of 2,000? 1,680. And that's the type of thing companies do, because when you make large orders of anything, you have to know something's not going to come quite right or the way you want it, and you kind of work that into your expenses of things.
Sorry, this is just a question on what is it like 97?
The 0.7, if you see some of these and it'll say like, I think it's probably 99.7 is what it may come to. When you're getting very exact in statistics, the 99th percentile that we talk about here actually goes all the way to 99.7. But for a generic statistics purpose where you don't want to get into all the extra decimals, most of the time it gets rounded back to the 99. So if you see 99.7, treat it like the 99. Treat it like 3 deviations each way. Oh, well. So, but that's how that one would work its way out. And then we're going to run into, I have a feeling, the same sort of thing here on number 9. So a lineup for tickets to a local concert had an average, or mean, waiting time of 20 minutes with a standard deviation of 4 minutes. What percentage of the people in line waited for more than 28 minutes? How many deviations am I going to be moving from my mean at 28 minutes? Okay, so we're going to be at a +2 standard deviations. Okay, so that cuts all this off. So, oh, and it's what percentage. So what percentage of people are waiting more than 28 minutes? 2.5. But here comes the application again. If 2,000 ticket buyers were in line, holy cow, how many of them would expect to wait for less than 16 minutes? Which direction and how many am I going with my deviations when I'm starting at a mean of 20 and getting down to 16? Okay, we're going to be left 1 deviation because 20 minus 1 deviation of 4 to get us to 16. So, okay, there's my 1 deviation, and less would be to the left. So what percentage of ticket buyers are going to wait less than 16 minutes? Okay, so 16% of them, and just like what we did in the last problem, number of people times the percentage tells us that about 320 of those people are going to be waiting less than 16 minutes. Actually apply it to what you're doing. So again, it's not bad. It's just getting used to, okay, what's the information and how am I trying to find it here? Where's it going to be? One last one. Sparklerific Sparkler Company is having an issue with their sparkler production. About 1/2% of the sparklers are only lasting 15 seconds, and about 2.5 are lasting only 30. How long does the average sparkler last? Any ideas on where to start with this one? What's that? Well, now that's true, but I do have enough information to kind of start figuring this out. So I start looking, I'm like, okay, 1/2 of 1%. And it's saying only lasting, so I don't think these are positive deviations we're talking about here. So 0.5, 3 deviations over, is lasting 15 seconds. Okay, let's do a little folding here. So I look at this and I say, okay, so here's my 15 seconds. All right. So it covers this. So here, basically, it's my 3rd deviation. 2.5%. Oh, the 2 and the 0.5 would be 2.5%. Are lasting 30 seconds, which basically looks like 2 deviations. If I want to find the average or the mean sparkler lasting, 2 questions. 1, what's the standard deviation look like it is? Okay, looks like the standard deviation is 15 seconds. So I know the 3rd, I know the 2nd, I want the mean. What's the mean going to be? Okay, 60 seconds or a minute, because if I went another 15 seconds, seconds, to get to the next deviation, when I get back to the mean, it looks like their average sparkler lasts 60 seconds. I don't have to have a lot of information to make these things work. I just have to know what to do with it. So basically what you're looking at is the types of questions I'm going to have on this nice quiz, we'll just call it, for tomorrow. There's 11 questions on it. Okay, and here's how I'm going to do this again. And I'll show you tomorrow when we're doing it. What I'm going to do as far as putting it in the grade book is there is going to be a column at the end of the grade book. 'Cause I know some of you check often and some of you maybe don't so much. I'm going to have a column in there that says makeup quiz. And it's going to be a 0 point, but over in the notation, if you improve, I'm going to say what quiz it was and what the score went from the old. So it'll literally go back into the gradebook and replace the old one, but there will be a notation in the gradebook of why it changed, when it changed, and what it changed from. But I'll show you that when we're done anyway.